Alright, hello everyone. You're welcome to week 1 lecture of PHY103 General Physics 3. The course is a 2-credit unit course, and as I explained in my introductory video, there will be 9 lecturers to take this course. So I will be the lecturer that will take week 1 topics: heat and temperature. Heat and temperature. So my name is Dr. W.A. Yahya. So in this topic, heat and temperature, these are the things I expect you to learn at the end of the class, at the end of the lecture. So I want you to learn the meaning of heat and temperature. I want you to learn the meaning of thermal equilibrium and what is the function of a thermometer. So then I want you to learn about the different temperature scales, the absolute Kelvin, absolute temperature scale of Kelvin, the Fahrenheit, the degrees Celsius scale, and so on. And lastly, how the dimensions of an object change as a result of an increase in temperature or a decrease in temperature, as the case may be. So these are the things I expect you to learn at the end of this class. So let's start with the concept of temperature. So temperature is actually a measure. So let me say it is a measure of the average kinetic energy. A measure of the average kinetic energy of a body. Kinetic energy of the particles of an object. Okay, so the temperature is actually related to kinetic energy. So later we'll see the mathematical relationship between temperature and kinetic energy. So the more the kinetic energy of an object, the more the temperature. The lower the kinetic energy of the particles of an object, then the lower the temperature. Now, how do we measure temperature? We measure temperature using thermometers. Thermometers. So they are used to measure temperature. So there are different kinds of thermometers. So one of them is the liquid in glass thermometer. Liquid in glass thermometer. So in this case, there will be a liquid in the glass. Like as it is shown here. So you have this glass, okay, then you have the liquid, which is red in color. So the liquid you're going to use in the glass should be a liquid that will have a different color with the glass, so that it will be easily visible when there is a rise in the temperature or there is a decrease in the temperature. Okay, so what you do is to use this liquid in glass thermometer, you note the initial reading. That's like the room temperature reading before you insert it into the object that you want to measure the temperature. For example, you want to measure the temperature of water or of a hot coffee, okay, or a hot tea. You want to measure the temperature, so you dip the thermometer in the coffee. So before you dip the thermometer in the coffee, so you can just note the level. So then when you dip it, then you dip it in the coffee or the hot tea, so you note the final reading. Okay, so usually the scales used for thermometers differ. So in some thermometers, the Celsius scale may be used. Celsius scale. So let me explain the different scales. Now, so I said we measure temperatures using thermometers. So if you are measuring, the scale of measurements can be the degrees Celsius scale. In the degrees Celsius scale, we take the temperature of boiling water as 100 degrees Celsius. Then the temperature at which the water freezes as 0 degrees Celsius, or the temperature at which the ice melts, okay, as 0 degrees Celsius. That is on the Celsius scale. Then on the Fahrenheit scale, or before the Fahrenheit scale, on the absolute scale, which is the Kelvin scale, so there is a shift. Okay, so instead of using 0, so we have 273.15 Kelvin. That is the temperature on the Kelvin scale, on the absolute temperature scale at which ice melts into water or water freezes into ice. Then the temperature at which the water boils will be 273.15 plus 100, which is 373.15 Kelvin. So you can easily derive a relationship between the Celsius scale and the Kelvin scale. Okay, so the temperature in Kelvin is actually the temperature in degrees Celsius plus 273.15. So if you know the temperature in degrees Celsius, then you can easily determine the temperature in Kelvin using this expression. So let me tag it as equation 1. So that is I've mentioned 2 scales now. Then the third is the degree Fahrenheit, the Fahrenheit scale, which is common especially in the US. In Nigeria, the weathermen, they often give temperature in degrees Celsius, so we're familiar with that. So but in some countries, so degree Fahrenheit is often used. So what is the relationship between degree Celsius and degree Fahrenheit? So on the degree Fahrenheit scale, so let me draw that here, degree Fahrenheit. So the temperature at which ice melts or water freezes is given as 32 degrees Fahrenheit, while the temperature at which water boils is at 212 degree Fahrenheit. So you may want to find the relationship between the Celsius scale and the Fahrenheit scale. So what you do is, for example, you have the temperature in Fahrenheit and the corresponding temperature in degrees Celsius. So let's call that TC. So how do you convert, if you are given the temperature in degrees Celsius, how do you convert it to degree Fahrenheit, or how do you convert the temperature from degree Fahrenheit to degrees Celsius? What you can do is you can say from here to here, the distance from here to here is the same as the distance from here to here. So TF, that's the temperature in degree Fahrenheit, minus 32 must be equal to the temperature in degrees Celsius minus 0. Okay, so this from here to this point, then from here to this point. So the temperature in degree Fahrenheit is here that I want to measure, that I want to determine, is here. Then the temperature on the Fahrenheit scale at which ice melts into water is 32, so minus 32. Then on the Celsius scale is minus 100. Then again, if you find the distance, the difference between the upper point here and the lower point here, so that is 212 minus 32. So if you say 212 minus 32, then you also say 100 minus 0. So 100 minus 0. So we can write this expression as TF minus 32 equals TC. So let's call it equation 2. Then in this case, 212 minus 32. So 212 minus 32. So that is 180. Okay, so 212 minus 32. So this will also give us 180. Then equals 100. So let's call this equation 3. So you have to solve these two. I mean, they are coupled equations. So you can say you can cross multiply. Okay, so you multiply TC by 180. So 180 multiplied by TC equals 100 into bracket the temperature in Fahrenheit minus 32. Or you can say TC, temperature in degrees Celsius, because you divide through by 180, 100 over 180 into bracket T, temperature in degree Fahrenheit minus 32. Okay, so and this can be written as 5 over 9 into bracket TF minus 32. So it means if you are given temperature in degree Fahrenheit and you want to convert to degrees Celsius, you use this formula that the temperature in degrees Celsius equals 5/9 into bracket the temperature in degree Fahrenheit minus 32. So let's call this equation 4. Okay, so this is an important equation, so let me circle it. And what if you are given a temperature in degrees Celsius and you're asked to find the equivalent temperature on the Fahrenheit scale? So it's very simple. What you need to do is you make the temperature in degree Fahrenheit the subject of the formula in equation 4. You make it the subject of the formula. So if you make the subject of the formula, you obtain that the temperature in degree Fahrenheit is 9/5 the temperature in degrees Celsius plus 32. So please, you need to take note here. In this equation 5, the TC, temperature in degrees Celsius, is multiplying 9/5 before being added to 32. But in equation 4, you subtract 32 from the temperature in degree Fahrenheit before you multiply by 5/9. So if you know any of these two equations, if you know equation 4 or equation 5, if you know equation 4, you can easily obtain equation 5, and if you know equation 5, you can easily obtain equation 4. Okay, let me give a simple example. So let me call it a simple example. So the example is that convert 98 degrees Celsius to degree Fahrenheit. Okay, sorry, let me write it to degree Fahrenheit. So that is degree Fahrenheit. Then Roman figure 2. So let me just make this question 1, simple example 1. So how do we solve this? So this is very simple. So you have to convert from degrees Celsius to Fahrenheit. So what you do is you use equation 5. You use equation 5 so that the temperature in Fahrenheit scale will be 9/5 the temperature in degrees Celsius plus 32. So in this case it will be 9/5 multiplied by TC, which is 98 degrees Celsius, then plus 32. Okay, so what is that? So you can use your calculator. 9/5, 9 divided by 5 multiplied by 98, then plus 32. So that is 208.4 208.4 degree Fahrenheit. Okay, so it means 98 degrees Celsius is equivalent to 208.4 degree Fahrenheit. So the second part of the simple problem is that the question says oxygen freezes at minus 362 degrees Fahrenheit. So the question is, what is the Celsius equivalent? What is the Celsius equivalent of this temperature? So what you do here is to use equation 4. Okay, so you convert degree Fahrenheit to degrees Celsius. So in that case, you use TC equals 5/9 into bracket TF minus 32. Okay, so that you now have 5/9 into bracket TF, which is minus 362. Okay, minus 362, then minus 32. So again, you press your calculator. 5/9 multiplied by minus 362 minus 32. So you obtain minus 218.889. So that's approximately minus 218.9 degrees Celsius. Okay, I believe that's clear enough. All right, Zeroth law of thermodynamics. Zeroth law of thermodynamics. So let's say we have two objects, A and B, three objects, A, B, and C. Now this the black color here, the black rectangle here, denotes an insulator. So an insulator means it will not allow the flow of heat. It will not allow the flow of heat. So A and B are insulated from one another. Now, but there is a conductor between A and C, and that conductor between B and C. So Zeroth law is explaining that if A is in thermal equilibrium with C, what does it mean of thermal equilibrium? It means A and C have the same temperature. So initially A had maybe temperature TA and C had temperature TC, but since they are together and they are connected by a conductor, so at a point in time there will be exchange of heat from the body with higher from the body that has higher temperature to the one with lower temperature. So this exchange of heat will continue until the two objects have the same temperature. So at this point we say the two objects are in thermal equilibrium. Thermal equilibrium. Okay. Now, so if A is in thermal equilibrium with C, and B is also connected to C by a conductor, so there's exchange of heat between B and C, and B is also in thermal excuse me, and B is also in thermal equilibrium with C, then the Zeroth law states that A and B are also in thermal equilibrium. A and B are also in thermal equilibrium. So let me write the Zeroth law. All right. So if C is initially in thermal equilibrium with both A and B, then A and B are also in thermal equilibrium with each other. So this principle, this law, is called the Zeroth law of thermodynamics. Why is it called the Zeroth law of thermodynamics? It is called Zeroth law because it was discovered after the first and second and third laws of thermodynamics were discovered. So, but the importance was well established, so they had to give it the Zeroth law of thermodynamics. Alright, so the next concept I want to explain is specific heat capacity. What does it really mean? So if you take, let's say we have our thermometer. Our thermometer is graduated, so this is let's say this is 1 degree, the second degree, the third degree, the fourth one, the fifth one, the sixth one, seventh, eighth, ninth, and so on and so forth. Now if you bring water, if you insert this thermometer in water, so let's say we have water here, the thermometer is immersed in the water, and you also have another liquid, okay, or let me just say you have a metal like aluminium. So if you add the same energy, let's say you had 1 kilocalorie of energy to water and aluminium, the same amount of energy, the temperature rise in the two will be different. But you added the same quantity of heat energy to the two, but they will respond differently to that temperature. So water will rise by 1 degree, while this aluminium will rise by approximately 4.5 degrees Celsius on the Celsius scale. Okay, so they will respond differently with the same amount of heat energy supplied to them. So they have a property that we call the specific heat capacity. So it is different for different objects. Water, for example, water. So the symbol that we use for specific capacity is small letter C. Small letter C. So for water, the specific capacity is around 4185 joules per kilogram per degree Celsius. Okay, so let me remove this minus. So 4185 joules per kilogram per degree Celsius. So that is the specific capacity of water. If you compare it to the specific capacity of ice, is it's 2090 joules per kilogram degree Celsius. So water has higher specific capacity than ice and steam. Okay, steam also has a lower specific heat capacity compared to water. So this concept, that is the way, the rate at which an object responds to heat that is supplied to it, is a property that we call the specific heat capacity. Now, if let's say the quantity of heat that you supply, okay, you supply certain quantity of heat So quantity of heat energy supply, let's term it as Q, and you add this quantity of heat to an object of mass M, and that object has specific heat capacity of C. So if you add this quantity of heat, there will be a change in temperature, okay, from the final temperature, from the initial temperature to the final temperature. So let's call that delta T, so as the change in temperature. So if you add heat, then it will be an increase, then if you remove heat, then it will be a decrease. So there's a relationship between the quantity of heat that you add and the mass of the object, specific capacity of the object, and the change in temperature. So we have this beautiful formula, Q equals mc theta. So let me call this equation 6. Equation 6. Okay, Q equals mc theta. So if you know the specific capacity of a substance, of a material, or of a liquid, and you measure the mass, and you want to increase the temperature from an initial temperature to a final temperature, then this is the formula that you use to calculate the quantity of heat that you require. Okay, for example, you want to take a shower and it's cold, so you need a hot water to shower. So let's say you need the temperature, the water temperature, initial water temperature is let's say Ti, and you need the temperature to be increased to Tf. I don't know, maybe 60 degrees Celsius should be okay to take a bath. So we know the specific capacity of water, okay, it's 4185 joules per kilogram per degree Celsius. So if you know the mass of the water, then this is the quantity of heat that you need to supply to increase temperature from that initial temperature to the final temperature that you want. You use this formula, the mass of the water, or the quantity of water that you are using, multiplied by 4185 joule per kilogram per degree Celsius, then multiplied by this change in temperature, which is the final minus the initial. So this delta T is the final temperature that you desire minus the original, that's the initial temperature of the water. So let's take a simple example. Alright, so let's take this simple example. How much heat must be added to 3 kilograms of water to raise its temperature from 20 degrees Celsius to 80 degrees Celsius? So we use equation 6. So we say Q equals mc, the change in temperature. So m is the mass, which is 3 kilogram. C is the specific capacity. In this case, it is given as 4.185 kilojoule per kilogram degrees Celsius. It's the same thing as 4185 joule per kilogram per degree Celsius. The same thing. So 1 kilojoule is 1000 joules. 1 kilojoule is 1000 joules. So multiply by the change in temperature, so that will be 80 degrees Celsius minus 20 degrees Celsius. So 80 minus 20, that is 60. So let's take out our calculator. So 3 multiplied by 4.185, then multiplied by 60. So that will be 753.3. So 753.3 kilojoule. Okay, kilojoule. Or you can write it as 7.533 times 10 to the power 5 joules. Okay, so kilojoule is 1000 joule. So with these two, let's mark this. Okay. Now, so that is about that. So let me give. I'll give the exercises later. Okay. So these are the first two exercises. So exercise 1: to a 1 kilogram sample of wood, 40 kilojoules of heat is added, and its temperature is found to rise from 20 degrees Celsius to 44 degrees Celsius. So the question is, what is the specific heat capacity of the wood? So this question wants you to determine. So this is a way so to experimentally determine the specific capacity of a material. Okay, so you measure the mass of the material, then you note the amount of heat energy that you are supplying, you note the initial temperature, you know the final temperature. So then you use that formula, Q equals MC delta theta. So you make C this way of formula. So from that you can determine the specific heat capacity of the material. So the second example, the second exercise, in preparing tea, 600 grams of water at 90 degrees Celsius is poured into a 200 gram china pot. So the specific heat capacity of the china pot is 0.84 kilojoule per kilogram per degree Celsius at 20 degrees Celsius. So the question is, what is the final temperature of the water? So these are the two exercises that you should try that are related to the specific heat capacity. Okay, so next is expansion of solids, liquids and gases. So if you have a solid object, so let's say this is a solid object, the original length is L naught. That's if you measure the length from this point to this point is L naught. So if you subject this object, okay, or this rod of length L naught to an increase in temperature of delta T, so that is, you add certain heat to increase the temperature from the initial temperature to final temperature. So the difference in temperature is delta T. So it is found that this object will slightly increase in length. So there will be an increase in the length of this object. So this increase in length of this object is approximately, okay, proportional to the original length of the object and the increase in temperature. Okay, so the proportionality constant here is alpha. So alpha L naught delta T. So this alpha, although it is mathematically is the proportionality constant, it is called the coefficient of linear expansion. Coefficient of linear expansion. The coefficient of linear expansion. So you can, so if an object has original length L naught, so and you add heat, you measure the initial temperature, so you add heat so that the temperature changes to a final temperature, so you measure the difference in temperature. So when the object changes, you note the original length of the object and the final length as well. So if you measure that and you find the difference, this alpha will give the coefficient of linear expansivity for the material, the coefficient of linear expansivity for that material. And this coefficient of linear expansivity is a constant for a particular material. For example, for aluminum, aluminum, so this alpha is 2.55 times 10 to the power minus 5 per degree Celsius, okay, for aluminum. So it is 2.55 times, so it is constant for all aluminum. For brass, alpha is 1.93 times 10 to the power minus 5 per degree Celsius, and so on and so forth. For glass, okay, it is 0.33 times 10 to the power minus 5 per degree Celsius. So it is constant for a particular material. So let's take an example on this before we move on. Alright, so the example is a copper bar is 80 centimeters long at 15 degrees Celsius. So the original length L naught is 80 centimeters. The initial temperature, let's call it T1, is 15 degrees Celsius. So the question is, what is the increase in length? What is delta L when it is heated to 35 degrees Celsius? So T2 is 35 degrees Celsius, and we are told that the linear expansivity is alpha for copper is 1.7 times 10 to the power minus 5 per degree Celsius. So what we do, we have to calculate delta L, so we use delta L equals alpha L naught delta T. So what is alpha? Alpha is 1.7 times 10 to the power minus 5 per degree Celsius multiplied by the original length 80 centimeters. The original length 80, so let's convert that to meters. So 80 divided by 100, so that will be 0.8 meters. Then multiplied by the change in temperature. Change in temperature will be 35 degrees Celsius minus 15 degrees Celsius. Okay, T2 is 35 while T1 is 15 degrees Celsius. So if you take out your calculator and you multiply again, so let's take out our calculator. So we have 1.7 times 10 to the power minus 5, then multiply by 0.8 multiplied by 35 minus 15. So that will give us 0.0, that is 2.72 times 10 to the power minus 4. So 2.72 times 10 to the power minus 4 meters. So that is the increase in length. Okay, so the question says what is the increase? So how long will the object increase in length? That is, so the increase in length will be 2.7. So if you want to know the final length, so you need to add this 2.72 times minus 4 meter to 0.8 meters. So the original length is 0.8 meters. So T2, we can say, sorry, L2 will be 0.8 meters plus 2.72 times 10 to the power minus 4. It's a small increase. It's a very, very small increase in length, but there is an increase in length. Okay. So the next is area expansion. Area expansion. Area expansion. Now, what is this all about? If let's say we have an object. This is the dimension of the object. So there's the length, then there is the width of the object originally. Now this object now, so we now add heat. This object, we add heat and it increases. Of course there will be a slight increase. Okay, let's say it increases uniformly, so it's an isotropic material. So this is the original, this green is the original dimension, original area. Then from this green up to this red is the final area. So we also find out that the increase in area, similar to the case for linear, for length. Okay, so that the increase in area is also proportional to the original area multiplied by the increase in temperature. So in this case, the constant of proportionality, I'll denote it as beta. Yeah, so A naught delta T. Okay, so this beta in this case is called the coefficient of area expansion. Coefficient of area expansion. So let me tag this as equation, I think equation 7. Yes, equation 7. So let me tag this as equation 7. Now, if an object is isotropic, an object is an isotropic solid, what does that mean? It means it expands equally in the same in all areas, in all directions. Okay, so the increase this from year to year is the same as from year to year. So we say that object is what? Isotropic. So for an isotropic solid, okay, what does that mean? So it expands in the same way in all directions. So when we have an isotropic solid, the coefficient of area expansion beta is approximately twice the coefficient of linear expansion. So beta is approximately 2 alpha for an isotropic solid. Now we have the same thing for volume expansion. For volume expansion, so this one will involve a three-dimensional object or a liquid. Can be a liquid, gases, or a three-dimensional object. So in this case, so here A naught is the original area, so then delta A is the increase in area. So for the volume, so V naught will be the initial volume. Okay, then the change in volume when there is an increase in temperature, delta T, is given as a constant multiplied by V naught multiplied by change in temperature. So that constant, I will denote it as gamma here. So gamma here is the coefficient of volume expansion. Coefficient of volume. Again, for isotropic solids, so this gamma is approximately 3 alpha. This gamma is approximately 3 alpha for isotropic solids. Okay, so let's take an example. Alright, so this is the example. A 200 cm cube glass flask is filled to the brim with mercury at 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised from 20 degrees Celsius to 100 degrees Celsius? So we are given the coefficient of linear expansion of glass to be 0.4 times 10 minus 5 per Kelvin or per degree Celsius, and we are told that the coefficient of volume expansion of mercury is 18 times 10 raised power minus 5 per degree Celsius. So the question is very simple. So we are told that there is a glass flask. So let's say this is a glass flask. Okay, or let's say it is thin. Okay, it is now filled with mercury. So it is filled with mercury. So of course they are in thermal equilibrium. So the mercury is in thermal equilibrium with the glass, so they'll have the same initial temperature. So the initial temperature T1 is 20 degrees Celsius and the final temperature T2 is 100 degrees Celsius, so that the change in temperature is 80 degrees Celsius. So the question is now, if you add heat, if you increase the temperature to 100 degrees Celsius, what happens? This mercury will increase in volume. Okay, why? Because of this formula. So I think I've 7. So this will be equation 8. Because of this equation 8, okay, the mercury will increase in size, but the glass will also increase in size. So you can say, one can claim that since the glass will also increase in size, so you should be able to accommodate the increase in volume of the mercury. But you have to consider the coefficient of volume expansion of the two. Now, if we take the glass to be an isotropic material, then the coefficient of volume expansion of the glass will be 3 times that of the linear expansion. So that will be 3 multiplied by 0.4 times 10 raised power minus 5. So, and that will be 1.2 times 10 raised power minus 5 per degree Celsius or per Kelvin. So if you compare this value 1.2 for the glass, coefficient of volume expansion for the glass is 1.6 minus 5, while the coefficient of the volume expansion for mercury is 18 times. So the mercury will expand faster than the glass. It will expand faster than the glass because of this high value of volume expansion. So at the end of the day, there will be the change in volume of the mercury will be greater than the change in volume of the glass. Okay, so the difference between these two will be the quantity of mercury, the amount of mercury that will overflow. You know, the question says how much mercury overflows when the temperature of the system is raised to 100 degrees Celsius, because mercury will expand faster than the glass. So the difference between the volume of mercury and the volume of the glass will be the volume of mercury that will overflow. And we are going to use equation 8 for the two. So that gamma V naught delta T. So this will be gamma for mercury, the initial volume, then delta T for mercury, minus gamma for glass, initial volume. They both have the same initial volume because the mercury fills the glass. So the initial volume is 200 cm cube. So they also have the same initial temperature and the same final temperature. So the only thing that is different here is the coefficient of volume expansion for the two. So we can say V0 is common, delta T is common, into bracket the coefficient of volume expansion for mercury minus the coefficient of volume expansion for glass. So we are told that the initial volume is 200 cm cubed and the change in temperature is from 20 to 100, so that will be 80 degrees Celsius, and the coefficient of volume expansion of mercury is given as 18 times 10 raised to power minus 5, while the coefficient of volume expansion for glass, we calculated that to be 1.2 times 10 raised to power minus 5 per degree Celsius. So if you take out a calculator again, you shall see, so 200 multiplied by 80, then multiply by 18 times 10 raised to power 18 times 10 raised to power minus 5, then minus 1.2 times 10 raised to power minus 5, close the bracket. So you obtain 2.688. So that's approximately 2.7 cm cube, because this degree Celsius will cancel the per degree Celsius, so you'll be left with 2 with cm cube. So the volume of mercury that will overflow will be 2.7 cm cubed. So yeah, so this is where we stop for this week's class. So I will give an exercise. So if later this video lecture will be uploaded to the course LMS, so there will be opportunity for you to ask questions. So if you do not understand the particular concept, so I urge you to watch this video. I will also upload this note handwritten notes, and I will also upload the typed notes. So I've typed a certain note, so I'll upload the notes with these handwritten notes. So if you have a question, so you are free to ask us. All right, okay, let me quickly give you the exercise. Okay, so this exercise for expansion of solids, liquids and gases. So how much water overflows when a Pyrex vessel filled to the brim with 1 liter of water at 20 degrees Celsius is heated to 90 degrees Celsius? The coefficient of volume expansion of Pyrex and water are 9.6, 9 times 10 to the minus 6 per degree Celsius and 2.1 times 10 to the minus 4 per degree Celsius respectively. So the question is similar to the example that we did. All right, so thank you.